Hello? Hello. All right. Hello, everyone. I'm Han from Yale University, and today I'll talk about the instabilities of core streams, including the KHI and the KHI and the effects of the other physical effects like the gravity and cooling. So to introduce a little bit about core streams, like the massive galaxies at the high redshift, like larger than like galaxy mass by like 10^12 solar mass at like redshift of like more than 2. These have the core streams penetrating from the cosmic webs and feeding into the halo and serve as the main mode of the equations. So the question is, how far can these gas streams penetrate into the halo? Because these streams can be disrupted while on their way to the galaxies, for example, like shocks, different instabilities, and it can collide with the other streams, and so on. So one of the things that we'll focus on here today is the Kelvin-Helmholtz instability, which can occur when you have a shearing motion between the two different gas medium. So you can estimate some of these parameters of the gas streams through some simple Twine model. For example, you have the hot halo gas around like 10^6 Kelvin, and then you have the core streams of like about 10^4 Kelvin penetrating. So you have about a factor of 100 difference in the temperature, which can translate to the factor of 100, 10 to 100 in the density contrast. You can also estimate the inflow speed of these gas streams by assuming some cosmological inflow, and then you will find that these streams are like supersonic with respect to the hot halo gas. So some of the simulation results from by just looking at these streams and the simple hydrodynamics shows that some of these gas streams can be disrupted by the Kelvin-Helmholtz instability, as you can see from these slides. Like as you go forward, like the mixing layer grows and the stream got disrupted. So some of the main conclusion is that within the various sound crossing time, if you have the stream radius of like less than 5% of the radial radius, also the streams can get disrupted, and up to like 50% of the kinetic energy from the streams can be lost to the background, and this power can also be comparable and like to the power that you observe from the alignment alpha observations. These nonlinear effects, the nonlinear evolutions of the KHI, like stream disruption and the deceleration, can be analytically predicted from to estimate some sort of time scales for these. Also, the other thing about after the KH instability takes over, the streams will get disrupted and they get fragmented And so these clumps that form from the KHI can also be used to explain some of the clumps that is seen in the simulations and the observations. For example, like the kind of observations seeing like some sort of gas clumps, but also like some cosmological simulations also show the formations of these clumps. But you have to take into account like physical effects such as gravity and the cooling to actually interpret these results, because like gravity can collapse, can cause these clumps to collapse. Cooling can cause the condensation onto the clumps and so on. So the thing that I will mainly focus on is the KHI plus the soft gravity. So for the streams to be in the hydrostatic equilibrium, the mass final length of the stream must be lower than some critical value, which is obtained as one of the classical results by like Ostrager 1964. And this value is given for the isothermal stream, but you can also derive it for the other polytropic index, of course. If you have the mass final length that is higher than this critical value, then the stream will not have enough pressure to counteract the gravity, and so it will collapse. However, even if the mass final length is less than this critical value, the gravitational instability can still take over to form clumps. some sort of, this is related to the, say, some surface modes when you have the different density contrast at the interface of the streams, the gravity can, gravitational instability can grow. And the growth rate of this, the maximum growth rate has been estimated by these people from like Hunter and Nagasawa. So when you have both this gravitational instability and the KH instability, you can compare the time scale for the gravitational instability to take over, or you can and compare that to the time scale for the shear layer to grow in the following the KHI instability, to see which one can dominate the eventual evolutions of the streams. So you can compare this like Tmax T shear in the shear in the y-axis, x-axis is the mass by unit length, and you can see that at some the point when the two time scale will be equal is the critical mass by unit length, where the regime will switch from one to the other. For example, if you have if you take less time for the KHI instability to grow, then the KHI, the shear layer will disrupt this density contrast before any gravitational instability can grow, and so KHI will take over, and vice versa. So this is one of the results when the mass by unit length is very high, and so the time scale for the gravitational instability is a lot lower, and so so what you see is the clump formation. So the left panel shows the streams with the no gravity, and you can see that you can see the formation of the mixing layer due to the KHI and the formation of small fragments at the end. But if you go to the one with the gravity in the middle panel, you can see formation of big clumps at the center of the streams instead of the KHI disruption. Even if you go to like a lower mass by unit length, still greater than the critical value, you can see this formation of blobs at the center of the streams. And you can see that the mass by unit of 0.9 and mass by unit of 0.4 have like different clumps. Like these clump properties that forms after the soft gravity depends on the mass by unit length. So if the mass by unit length gets larger, more gas from the streams will remain inside these clumps, and so the top left panel shows the mass inside the clumps normalized by the mass inside the streams, and you can see that as you go to the higher mass by unit length, more gas remains inside the clumps. Clumps are also more turbulent if you go to a lower mass by unit length, which you can see on the top right panel. But also because the mass by unit length is lower, the confined pressure of the pressure is also larger. So that can be seen in the comparison between the two visualization parameters on the bottom left. On the other hand, if you have if your time scale for the KHI to grow is faster, then the stream will get disrupted. However, you can see the effect of the gravity. So the left panel is the no gravity, the right panel is the one with the gravity. And you can see that the stream remains kind of intact like after like async crossing, you can see some of the stream structure at the center when you have gravity. This is because of the buoyant force that stops the mixing between that stops the growth of the mixing layer. Like HS characterizes the width of this mixing layer, and for the dashed line, all the dashed lines for the no gravity run goes to the 1, which means that all the stream get eventually disrupted. But for the one with the gravity, all of them stops around like 0.5 of the stream radius. This is because of the buoyant force that stops the mixing between the two different media. So you can characterize this buoyant force using the Richardson number, which compare the buoyant force to the turbulent mixings. And yeah, if this Richardson value is greater than like some critical value, in this case like 1/4, that means that buoyant force is larger and it can stop missing. So you can see that after this Richardson value gets greater than this 1/4, most of the early growth of the mixing layer stops and like gets sourced out. So this is the working prep. So what happens if you add some sort of dark matter gravity in addition to the self-gravity? Well, it usually just amplifies the effects of the gravity and increase. For example, if you are looking at the gravitational instability dominated regime, the gas mass that goes into the clump will get larger. And if you go into a KHI dominated regime, the Richardson number gets larger. But in the middle, it may also shift the critical mass particle length. The other thing that I also talk about is the cooling. This is the work by led by the Neil Monaco here. And so the left-hand side is the one with the no cooling. Right-hand side is the one with the cooling. And in these simulations, the important parameter is the cooling time in the mixing region. If this cooling time is less than the disruption time, then the cooling is effective. And you can see the difference between these two panels. So the main thing is that when you have KHI, the stream expands into the background, and the stream density is reduced. But on the other hand, if you have cooling, because when you form the mixing layer, the gas cools down and then condenses back onto the streams. And so the stream remain dense. And then you can see the stream feature at like the H sound crossing time comparison. But however, even though they have different mechanisms, they both entrain mass equally, but also decelerate in the same manner. However, if you have the cooling time that is greater than the disruption time, then cooling is not very effective, so it is similar to the simulations without cooling. And so we talk about, and so because the background is condensing into the streams when the cooling is efficient, the cold gas mass in the gas streams can be increased by a factor of up to 2 to 3 times the original values. And you can also see the energy radiated, which is mostly comes from this cooling of the hot gas. And you can also see one line in the mass plot. When it goes down, this is the simulation when the cooling time is larger than the disruption time, so the cooling is not very effective. So in conclusion, both the gravity and cooling are important in the eventual evolutions and the disruptions of these cold streams, cold dense streams feeding the massive galaxies, in addition to the KHI. So both cooling and the weak gravity can reduce the stream disruption for different reasons. And it can enable the streams to penetrate farther into the galaxies and feed farther into the halo and feed the galaxies in the center. The gravity also plays a critical role in the formation of clumps in these massive galaxies, especially when you have the high mass particle length. So for future walks, well, when we talk about gravity, these streams are penetrating into these massive halos, so it is also important to include the external halo potential, which can speed up accelerate the stream as you go inward, and also can, so because of the different geometry, you have the stream radius gets lower and lower as you penetrate farther into the center. Also, when you have this formation of clumps in the gravity, if you add cooling, these properties can change as well. So like the other goals is to combine this cooling and gravity. But also, we will also plan to compare this to these streams in the hydrodynamic cosmological simulations to understand further how feeding and the clump formation process happens in these high-Z clusters, and possibly to estimate the effects, but also to see if they resolve these effects or not, and if they don't, then do they overestimate or underestimate these effects? Thank you.
For questions for Han, starting with any students or postdoc. If not, any faculty member or senior colleague? Okay. Can I ask you one question about how can we actually go about test these, make connection to observations? Can you actually use the Lyman alpha emissions as a way of actually testing some of these physics? Yeah.
Well, so for example, like, when you have the cooling in the simulations, like this is a work done by Niyamanaga. He has calculated the radiated energy, and then you can actually compare this radiated energy to the energy that is observed in the Lyman alpha blobs, and see if they are comparable or not. And currently, I believe the results are promising. So.
All right. Any other questions? If not, let's thank Han again. Okay, so we're going to break. Before we break for